Okay, for problem number 1, we want to know what's the probability of choosing a vowel. So we want to go ahead and put our answers in fraction, decimal, and percent form, and then we want to identify the likelihood statement. So is it impossible, unlikely, equally likely, likely, or certain? Remember, if it's impossible, it means it has a 0 chance of happening. If it is equally likely, it means that it has 50% or half of a chance of happening. If it is certain, it means it's 100% chance or 1/2 of the probability happening. Unlikely is between 0 and 50%. Likely is between 50 and 100%. So we're looking at those values there. All right, so choosing a vowel in the alphabet. Choosing a vowel in the alphabet. So we know we always want to set this up as the event over the total. So the event that we're looking for is to land on a vowel. Vowels are A, E, I, O, U. Okay, those are our vowels out of all the letters in the alphabet. So how many vowels are there here? 5. How many letters are in the alphabet? 26. So we have 5 over 26. There's our fraction. Now remember, to convert a fraction into a decimal, all we have to do is take 5 and divide it by 26. And we're going to go ahead and round it to the nearest, we'll say thousandth. We'll do nearest thousandth for that one. And that's going to come out to 0.192, which is going to come out to 19.2%. So here's our fraction, here's our decimal, here's our percentage. Now what's our likelihood statement? Is this impossible? Does it have 0% chance of happening? No. Is it unlikely? Yes. This is an unlikely event. Unlikely because of the fact that it is greater than 0, but it is less than half. So it is unlikely to occur. There's your fraction, decimal, percent, and your likelihood statement. Number 2, the probability that we're going to land on orange. So we've got a few colors here. We've got pink over here and over here. There's our pinks. We have some blues. We have a blue here, a blue located here. We also have some greens up here, a couple of greens. And then we do happen to have an orange. Okay, so based off of here, how many oranges? So remember, we're going to set it up as the event, which happens to be orange, which happens to be just one orange. There's only one orange out of the total, which happens to be the all sections, right? All the sections on the spinner. How many sections are on the spinner? 8. So there's our fraction. Our fraction is 1 over 8. If we were to convert that into a decimal, that's going to be 0.125. If you do 1 divided by 8, you're going to get 0.125. If you multiply that by 100, that gives you 12.5%. What kind of likelihood is that? Unlikely. It's not impossible. Impossible means it's 0. Is that 0? Is that 0? So if I ask you, would you like to have $12.50 or $0? Which one are you going to go for? 12. 12 is not the same thing as 0. Okay, if I say I'm going to give you 12.5% extra credit versus 0% extra credit, are those the same? No. 0 and 12.5 are not the same. Okay? I can't tell you how many times when it says it's going to have something like, oh, it's 12.5% chance of raining, and I think it's not going to rain, and it does. Okay? Still has the possibility of raining. Number 3, probability that a month is going to end in the letter W. Okay, so again, we're going to set this up as our event over our total. So the event is a month that ends in W out of all the months. We're looking for a month that ends in W out of all the months. What months end in W? None of them. There aren't any. That's 0 months. Out of how many months? 12. 0 out of 12. 0 over 12, which equals 0, which equals 0%. What kind of probability likelihood is this? Impossible. This is a situation that is impossible because it's exactly 0% chance. That's when we can say it's impossible. All right, number 4. We're going to roll a number that is less than 7 on a number cube. Less than 7 on a number cube. So here's a number cube. So the event I want is less than 7 out of the total. How many numbers are less than 7 on a number cube? All of them, right? 1, 2, 3, 4, 5, 6. All those numbers. There's 6 numbers out of 6 that happen to be less than 7. 6 out of 6, that's going to simplify to 1 whole, which is 100%. So what's the likelihood that this is going to happen? Certain. This is certain to happen. All right, number 5. We've got a bag of marbles. There's 6 red, 6 blue, 4 green, and 2 yellow. I want the probability of green. I want the probability of green, so I want to know the number of green over the total number of marbles. How many green are there? 4. There are 4 green out of how many total? We just have to add 6 plus 6 plus 4 plus 2. What do we get? 18. So we have 4 over 18. Now we need to simplify it. 4 over 18 can simplify. It simplifies to 2 over 9. And I'm going to leave it in this form because it doesn't tell me which form I need. So I'm just going to leave it in fraction form. 2 over 9 is the probability that green is going to happen. Now I want the probability that it's not going to be green. So if I know it is going to be green is 2/9, all I have to do is do the opposite of it. I just have to take the opposite of it. So 2 out of 9 are green. How many are not? 7 out of 9. 7 out of 9. Because notice 7 plus 2. What's 7 plus 2? 9. You're either green or you're not green. Now, you could also do it the same way that Christopher probably did it. He counted up how many were not green. Okay, not green means that it's going to be red plus blue plus the yellow out of all the total. Okay, and so we know, hey, this is 6 plus 6 plus 2. That comes out to 14 out of the 18. And then we can simplify it. When we simplify it, it simplifies to 7 over 9. So if you didn't know that green was 2 over 9, you had to actually find just not green. You would count how many are not green out of the total. All right, my last question for you guys. Eric's teacher almost always gives a quiz the day after a lesson that students don't ask a lot of questions. Should Eric expect a quiz on Thursday if no one asked any questions on Wednesday? So should he expect there to be a quiz, yes or no? Yes, he should. This is a likely situation. If we look here, he almost always is another way of saying that this is a very likely event to occur. This is likely to happen. Almost always is a likely event. If they do not ask questions, almost always there's going to be a quiz the next day. No one asked questions, so yes, this is very likely. Very likely to occur. So yes, he should be expecting there to be a quiz. Okay, let's go ahead and move on to the lesson for today. We're going to be talking about theoretical probability versus experimental probability. Theoretical versus experimental. Now, with theoretical probability, when we talk about theoretical, basically anytime that we have an item, like we've got a coin, or if we have, coin or a die, or the spinner, these all have probabilities of specific events occurring. So if I flip a coin, how many times do I expect to land on heads? Like 50% of the time, right? That's called theoretical. If I flip the coin 10 times, am I guaranteed to land on heads 5 and tails 5? No. Okay, same thing. When I roll the die, I have a theoretical probability, an expectation that I'm going to land on a 1 out of 6 times, right? 1/6 of the time, or roughly around 17% of the time. But if I reverse it here and roll it 6 times, I'm not guaranteed to land on a 1 and then land on a 2 and then a 3 and then a 4 and then a 5 and then a 6. Okay? I might land on a 1 multiple times, or maybe I don't land on a 1 at all. Maybe I land on a 6 every single time. You don't know. But in theory, theoretical probability is that idea, and none of you should have your computers open. Close them now. In theory, this is what we have come to expect. So we think of theoretical probability as what should happen. And I want to write that down. This is a probability of what should happen. It doesn't always happen, but it's what we have come to expect to happen. Now, real importantly, we also have to understand that there is no action. If I place a coin here and I say, hey, what's the probability of landing on tails? I don't have to actually flip the coin to know that the probability of landing on tails, theoretically, is supposed to be 1/2. And give a spinner, hey, I want the probability I will land on a 2. I don't have to sit here and spin it. I'm just going to look at the spinner and go, okay, there's one value that's a 2 out of 5 sections, 5 equal sections. So it's going to be 1 out of 5. Okay? So these are theoretical. No action, no flipping the coin, no rolling the die, no spinning a spinner. None of that actually has to happen. Okay? Let me write an example again. So for example, if I go ahead and roll a die, if I focus on rolling a die and I want the probability that the die is going to land on the number 2, that's going to equal 1 out of 6 because there's only one value on the die that has a number 2 on it. Okay, there's only one face on this die that has the value 2 on it out of 6 different sides on here. Okay. Again, if I flip a coin, and I want the probability that the coin is going to land on tails, that's going to have a theoretical probability of 1/2 because only one side of the coin is labeled tails out of the 2 sides. So 1/2. Okay, these are theoretical probability. Then we have experimental probability. With experimental probability, there is action. Action is required. And with experimental probability, instead of it being what should happen, with experimental probability, we call it what actually happens. You want to write this stuff down. This is going to be on your assignment today. What actually happens. Experimental probability is what actually is going to happen. There is action. Action is needed. Okay, you should be flipping the coin multiple times, rolling the die multiple times, spinning the spinner multiple times, at least 2 times, at least 2 trials is going to make it an experiment. Okay, at least 2 trials will make it an experiment. And with experimental probability, we focus not on Like if I want to spin the spinner, and theoretically I know it's going to land on a 2 1 out of 5 times, but then I'm going to actually spin it and say, okay, how many times am I spinning the spinner and how often does it land on the 2? Oh, I spin the spinner and it landed on 2 4 times. So the number of times that the 2 happened would be 4 times out of the total number of times that I spin the spinner. So those are different. It's still an event over a total, but now that's the action. How often did the event happen out of how many total trials, how many total experiments did you do? So for example, I'm going to roll a die 27 times, and it lands on the 2 8 times. I'm going to roll a die 27 times, and it's going to land on a 2 8 different times. So then the probability that it's going to land on a 2 is 8 out of 27. 8 times that it landed on a 2 out of 27 different trials. Okay, another one. If I flip a coin, I'm going to flip a coin 70 times. And it lands on tails 30 times. Then the probability of tails, based off of my experiment, is 30 over 70, which would then simplify. We can simplify it to 3 over 7. Okay, so your experimental probability is not always going to be the same as your theoretical probability. And the way that we like to look at it is we think of theoretical probability as the correct answer. That's the goal that you want to achieve. It's kind of like when you guys say, hey, I have a goal of making an A in a class. You work towards that. Or I have a goal of working out, 5 times a week. That's something that you're trying to achieve. This is the same thing. Theoretical probability is the goal in mind. You're trying to work your experiment until you can get to the theoretical's value. All right, go ahead and go to the next page. I'm leaving it. All right, so for here, this graph shows the results of an experiment in which a spinner with 3 equal sections is spun 60 times. We want the theoretical probability that we're going to land on red. So for the theoretical probability, what we're focusing on is the fact that we've got 3 equal sections. 3 equal sections, and we just want the theoretical probability for right now. A theoretical probability of landing on red. So if I'm talking about spinning a spinner, this table right here, this table is the results of an experiment. This table of information is the results of us performing an experiment. Spinning the spinner. So when they say spinner results, that means that they've actually performed the experiment. That's not going to be theoretical probability. That's going to be your experimental probability. So this table is going to be utilized for this question. So now I have to ask myself, okay, well, what am I utilizing for the theoretical probability? Well, they told me I have a spinner that is 3 equal sections. So I'm going to draw a spinner, and I'm going to split it into 3 equal sections. Okay, how do I know what the sections are labeled? How do I figure out what the sections are labeled? They didn't tell me what the labels were in the problem. Where can I figure out what my 3 sections are labeled? From the graph. What are my sections? Green, blue, and red, right? We've got a green section. That's what this bar represents, is the green. We have a blue section. And then we've got a red section. I'll just use the pink. Okay? And they're supposed to be equal in measure, so we'll pretend that they're equal. Okay? So we want the probability based off of the spinner. So what we need to do is we're going to focus on the spinner. I want the probability that it's going to land on red. So that means I'm looking for the number of red over the total sections. How many red do I see on my spinner? How many red? Come on, guys, wake up. How many reds? 1. There's 1 red on the spinner. How many total sections are there on the spinner? 3. So 1/3. 1/3 is going to be my probability. This is roughly around 0.333, which is roughly around 33.3%. So here's my fraction, my decimal, and my percentage. I like to convert them into decimals and percents because you guys have an easier time comparing decimals and percents. If I say, hey, compare 1/3 and, 1/4, some of you might have a little bit of a hard time understanding that 1/3 is bigger. Especially with yesterday's ticket out the door, a lot of you thought that 1/12 was bigger than 1/2 because you're looking only at the denominator. You have to think about it by comparing them in decimal form. Decimal form is a lot easier to compare, okay? All right, experimental probability. Now with the experimental probability, now we can focus on the results of the spinner. So now we're looking how many times. So if I'm wanting the probability of red for here, I want to know the number of times we landed on red. The number of times that we landed on red out of the total spins. Not the number of sections, not the number of colors, but the total number of actual spins that happened. So, how many times did we land on red? Look at your table. How many times did we land on the red? 24. We landed on red 24 different times. How many times did we spin the spinner? 60 times. One, it tells us in the question, right? You spun the spinner 60 times. But even if they didn't tell you in the question, we could just add up all the spins together. We could do 21 plus 15 plus 24, and that's going to come out to 60. So we get 24 over 60. Now, we could simplify this. They both happen to be divisible by 12. And that's going to simplify to 2/5. So we get 2 over 5, which is the same thing as 0.4, which is the same thing as 40%. So here's my probabilities for the experimental. So now I want to compare. We're going to compare experimental probability and the theoretical probability. Are they the same? Are they equal? Is 33.3% the exact same thing as 40? No. Our experimental probability, which is 40%, happens to be greater than our theoretical probability. Our theoretical probability, which is about 33%. Okay, they're not the same. Right now, our experimental probability is a little bit off. Okay, let's take a look at the next question. Here is a frequency table. Frequency tables are ways for us to tally how often a specific event occurs when we've performed an observation or an experiment. So this, again, this table represents the experiment that is occurring. So we're going to use that for our experimental probability. Then we're talking about theoretical probability. So in theoretical probability, that means we need to focus on an actual die. So an actual die has our 6 sides. So I'm going to just go ahead and draw a real quick cube so that I know, hey, I'm talking about a die that looks kind of like this. And we've got, 6 dots up at the top maybe. And then maybe off to the side we've got the 4 dots here. Okay, this is what my little number cube or my game die is going to look like. And this is what we use for our theoretical. We use the die for the theoretical. So in theory, looking at just the die without me rolling it, how often should I land on a 6? How many 6s are on here, Angel? 1 out of 6, right? The 6 only occurs one time out of 6 sides on here. So it's just going to be 1 out of 6. 1 over 6, if you were to convert that into a decimal, it's 0.16, and it keeps going, so around 0.167, which is about 16.7%. 16.7%. Okay? Now, experimentally, again, I want to focus on how often did I land on a 6. So let's take a look at the 6 right here. How often did we land on a 6? How many tally marks do we have for the number 6? 12, right? This is 5, this is another 5, plus another 2, so that's 12 different times out of the total. So now you need to add these up. So this is 7, 3, 3, 5, 2, 12, and if we add it all together, we're going to get 32. That's the total. We can simplify 12 over 32. They're both divisible by 4. They're both divisible by 4. That's going to come out to 3 over 8. And 3 over 8 is the same thing as 0.375, which is the same thing as 37.5%. Okay, so now we need to make our comparison. We're comparing our experimental probability of 37.5% to our theoretical probability of 16.7%. Which one's bigger? The experimental. Experimental happens to be bigger. Okay, now there's a reason as to why you're very rarely going to see them being the same. Very rarely are you going to see them being equal to each other. Experimental is usually going to be either greater or less than your theoretical, and it's because we're not performing enough of the experiment. Let me go ahead and talk to you about that in just a second. Go ahead and flip to the back page. We're going to do our own little experiment. Okay, we're going to perform our own little experiment real quickly. All right, so on the back here, we're going to go ahead and as a class, we're going to roll this die and we're going to document how many times we land on the different values, okay? So we're going to roll a single die and take note of all the outcomes. But the first thing I want to do is I want to make a list of all the possible outcomes. So let's make a list of all possible outcomes that a die can land on. What's the first one it can land on? It could land on a 1. We could land on a 2, a 3, a 4, a 5, and a 6. Okay, these are all the possible outcomes that we can land on. Now, I want to focus on the theoretical probability. In theory, how often should I land on a 6? So the probability of me landing on a 6, how many 6s are on the die? 1 of them. Out of how many again? 6. So 1 out of 6, which is roughly about 16.7%. Okay? So what we're going to do now is we're going to go ahead and roll them. We're going to roll it 10 times, and we're going to document how many times we land on a 6. Or, what do we land on? So the first one, we landed on a what?
3.
Okay, so for roll number 1, put down 3. Let's roll it again. We landed on a 2. Let's zoom out for this for a little bit. Okay, third time, we're going to land on a 5. So we've got 3, a 2, a 5. Let's go another one. 4. Let's do it again. 3. Do it again. Oh, 6. Okay, roll number 7 is a 2. Roll number 8 is a 3. Roll number 9 is a 4. Roll number 10 is a 4. Did we ever land on a 1? No, but a probability of landing on a 1 would be 1 out of 6, but here we didn't land on it at all. Okay, how many times did we land on a 6? We want the experimental probability of landing on a 6. So how many times did we get 6? 1 time out of how many total rolls? 10 rolls. That's going to come out to about 10%. Are they the same? No. So again, the reason that they aren't the same, the issue that happens is because we didn't perform this enough experiments. We need to perform this more times. Okay, so write that down. The more trials, the closer your experimental probability will become to your theoretical. Okay, the more times that you perform the experiment, the better. It's the same thing with everything you ever do. Like we talked about before with getting vaccines. If you get a flu vaccine, are you going to be comfortable getting a flu vaccine that was only tested on 10 people or 10 million people? 10 million. Okay? If you're picking somebody to play on a basketball team, do you want to pick somebody that has only spent 1 year practicing or 10 years practicing? Probably 10 years. Okay, a lot of times parents get a little iffy when they see that a teacher is brand new compared to their child having a teacher with more experience. Think of it. Experiment, experience. The more experiments, the more experience, the better. Okay? So let me show you that in mind.